But I'd now like to introduce Brian Harrington, who's a technical specialist with 20 years operations research and simulation experience at Ford Motor Company. He designs and implements manufacturing process improvements which incorporate many conflicting objectives such as robust, flexible, and lean systems, and will be presenting on a Six Sigma approach to simulation. So I'd like to go ahead and hand it over to you, Brian. So thanks for joining us.
Okay, thanks, Glenn. Okay, yeah, I'm Brian Harrington. I've had 20 years experience with Ford Motor Company, primarily all around simulation, different types of simulation from process-driven product design to discrete event simulation. My passion truly lies within discrete event simulation. Also, I'm a certified black belt, so I have conducted several Design for Six Sigma projects for Ford Motor. And currently, I've left Ford and I've started my own consulting company, Mountain Sim, and I'm located in the mountains of Whitefish, Montana. So today, I would like to talk about some of the lessons learned in my experiences of building models, especially for a large automotive company. So really, the theme is going to be some of these successful simulations using really the less is more approach, trying to get to the answers as quickly as possible, get the answers to management in a time that they can actually implement some of these and make important business decisions in a fast manner. So let's go ahead and get started. First of all, I'm going to set the scene up. This is a typical conference room. It looks like the management's showing that we're already 2 weeks behind schedule. We have some engineers talking about cycle times and catastrophic breakdown. In other words, there's a lot of information hitting the floor, hitting the conference room floor all at once. Different pallet types in the system. So what we have here is a typical scene of a tremendous amount of data coming in. This is when we're doing simulating or preparing for the next product change of a large manufacturing facility. This can be very much the scene, a chaotic scene of trying to get the program launched. So what this equates to is complex systems and a shortened development time. So what we're seeing here is a shortened development time to get your product to the market in the least amount of time. Well, what this is, it's a really good equation for stress. And what we often hear is, well, let's simulate it. And that's a great idea, but what that's just done is it's pushed the stress on the simulation team. So what I've learned is, when you're in these conference rooms, sitting back and hearing all this information, we know we're going to simulate it. Some of the techniques to filter through all this data and somehow make some sense of it and get to become the person at the table that not only has good questions, but actually starts providing answers, and answers quickly as possible. So this is the approach that we're going to take, and we're going to leverage some Six Sigma principles. In this short time that I have, I'm not going to dive into the great details of Six Sigma, but there are some fundamental concepts and tools in Six Sigma when applied to discrete event simulation models, especially early on in the process. It's going to definitely aid us in obtaining our answers, pertinent answers, quicker. So when we look at the Six Sigma, the DMAIC process, and we look at our typical discrete event simulation process steps, we see that they are very similar steps. DMAIC process is defining, measure, analyze, and improving and control your system. That's very similar to what takes place even when you go see a doctor. He measures your blood pressure, and they might analyze some things and give you some medicine, and you're going to control it over your blood pressure and so on. So there's even there, it's pretty fundamental steps that we've all even have experienced, even if you're not a black belt or a green belt. In discrete event simulation, we always want to start off with a sound objective. We want to have our assumptions, collect our data, and this can be very lengthy. This is the portion that I'm showing where we get a lot of data, particularly in manufacturing applications. And then, so ultimately, we're going to create and build this model. And in doing so, when we early on, if we can blend some of these, the methodology and concepts and tools of these two processes or steps of these Six Sigma and discrete event simulation, we'll see that these overlapping similar steps can really leverage the Six Sigma fundamentals to aid in your discrete event simulation modeling. So Six Sigma is really nothing more than, when you look at this transfer function, the transfer function really is just stating that the response or the output is nothing more than a collection of your inputs. So these inputs are referred to as our key input factors, or our X's. And usually these X's can be measured. Somehow they can be quantified. You know, they're going to be seconds or weight or something that can be quantifiable. A lot of them can be controlled, so they can either be measured and controlled. And when we do this, we can, the idea is when we control these, we're going to hone in on a particular output or response. But the important piece on this slide is really just that the fact that a system is really nothing more than a collection of its inputs. And what we see here is the inputs, we can quantify, or we can categorize them as N's and X's. And we'll really find out that a lot of the N's are really the trivial many. And so what it really comes down to is we want to be able to have some ability to hone in on the vital few. And when we push aside some of the trivial many, we can really start to focus on what those truly are the key inputs to drive this function. So when we step into discrete event simulation and we take this transfer function mindset, it's really the art and science side of modeling that comes out. Discrete event simulation is truly an art and science. We know that it has a science of logic and distributions and statistics and experiments or experimentation, but the art side is equally as important. So the art side usually comes out through experience. So as you gain experience, you can really start to sharpen the art side of modeling. So truly, experienced modelers tend to create models with the least amount of objects to meet their objective. And they'll refine their objectives as well, prioritize them. And by doing that, you can start to find out which are truly the trivial many. And once you start getting some of the ends or the clutter out of the way, it's easier to hone in on your analysis and your results. So a common modeling error is to say, when I simulate something, I have to put everything in it. You know, you put the kitchen sink in it. You put every nook and cranny, every event that's going to take place in this model, kind of like a recording of reality. It's truly, really, when we have shortened production times and so on, it's usually an equation that's not going to work out. So when we apply and we ask ourselves these two key questions, what is a significant input and how do I control it? This is a very important piece. And a simple tool that we use often in Design for Six Sigma projects is a parameter diagram. Now, a parameter diagram is similar to a cause and effect or a fishbone diagram. It's a diagram that annotates and categorizes our inputs into a system, and it offers itself as a diagram as an excellent communication tool for management as well, and the team for just organizing your overall input. But basically, the signal factors or inputs are your key inputs into the system. There are control factors. These control factors are the inputs that engineers or management can actually have control over. So it could be cycle times, it could be shift patterns, but things that we can actually control. Noise factors in the system are also inputs into the system, but they're generally things that we don't have control over. That might be some environmental factors. It very well could be marketing demand, things like that. Error states are inputs in the system. Those are our typical failure modes of the system, what causes the system to actually fail. And ultimately, we're trying to hit this response factor, or this what we refer to as the big Y. And really, it becomes your signal factors that are coming into the system can be transformed by your control factors to actually aid in hitting your precision and your accuracy of your response, and also reducing the noise factors and also reducing the error states. So when we start to look at and really concentrate on our signal factors and how the control factors can actually transform these to obtaining our target. That's really what it's all about here in a P diagram. And when we start to populate these, the teams shouldn't be too, they're overlapping, because it would be easy to say that some control factors are possibly noise factors. An example could be like a breakdowns. They're random. But someone might say, well, we can control these through preventative maintenance. As long as they're in a particular category, that's what's important. So it's always debatable on where they're going to land, or some of them, because it's not crystal clear exactly where. But as long as they're populated, it's an excellent place to start. So shifting a little mindset here, we're just now talking about, we're going to look at discrete event simulation. The basic building blocks when we're actually starting to conduct a model. The majority of my modeling at Ford Motor Company, I truly stayed with just my basic building blocks of work entry points or parts, buffers, storage areas, work centers, and conveyors. These basic building blocks, it's really just 6 is all you really need, because the work item types, they can represent not only just parts, but they can represent carriers, signals to other sections or submodels of the model. The important really key piece here is just I need that label profile. I need the ability to set labels. And when I do that, the work items can do that. So they can represent carriers or signals just as well as any other software package that actually has that object. But I like the sense that there's just 6 objects here that all I have to, the team of engineers has to work with. Activities, it's just the important piece here is it has the processor, the ability to have a cycle time. Storage areas, of course, they occupy space and contain the finite or infinite amount of width. Conveyors, moving from point A to point B, use these for even when we're modeling complex systems like electric monorail systems or power and free, power friction conveyors. Just simple conveyors used coupled with activities can accomplish the task. Resources, they can represent crews, forklifts, tugs. I've done a lot with that. Anything that requires the resource to be present. And then, of course, there are endpoints for freeing up the memory and collecting statistics. So stepping into some of these tools and applying some of this, if we just quickly look at a manufacturing example, this would be a problem statement of saying that if I had a sequencing bank and it had a finite capacity of 60 units, and the team was looking at a proposal of a 30% increase in throughput. So management want to know, do we need to add an additional lane, or can the sequencing logic, can we optimize our sequencing logic and get away with it just by doing that, by some of the internal moves? Maybe you have some designated lanes for product mix and so on. So if we look at this and we apply our 2 questions, what is a significant input and how do we control it, we would more than likely step into use our P diagram, and this is a heavily populated P diagram in the sense where I have the list goes on. So it's just an example of some of your typical inputs, and this list would go on. So you'd start off with a relatively heavily populated P diagram, and then the key input here would be we would try to get to answer this question as soon as possible. Does management really need to add additional lane, or can we solve this problem through improving our logic? And improving our routing logic would require additional detail and so on to get at. So the first thing that I would want to do is examine the system assuming perfect or ideal sequencing logic. By doing that, I've now eliminated quite a few of my n's and x's. They can be ignored. All this detail of the routing logic, of saying that a certain amount are designated to a certain lane and so on. All the complex portions of the model can be ignored for now. And what you can do is you're setting up some of the boundaries for this system. You're learning more. So the important piece here, you'd want to determine the breakpoint for where the system fails. So if the routing logic was perfect, you can just say that parts can come in and they can jump over each other and just hit into a certain lane and exit according to how they're getting called out. But the team can easily build a model with least amount of objects by ignoring quite a few of these pieces and actually find out where the breakpoint is. So if they were looking at a 30% increase, we might find out that a 23% is all it can take, and then after that it fails. The team then knows they need to add additional capacity. More than likely we're faced at putting in a new lane. And also, so what that has done is you're establishing credibility along the way. So you're providing these critical answers as soon as possible to management and to the team. So providing these initial answers even is a good way to keep the team engaged, because there's someone at this conference room table that's not only asking questions but is actually providing answers and boundaries of the system, is actually being able to funnel it in, channel the team to focus and keep going on where we need to go to get this product delivered. So in doing this, the simulation engineer learns more about the system, then he can keep the team focused on what really should be the pertinent next level questions, and therefore the next level set of X's and N's back into the system. So establishing credibility along the way is very key to modeling. You're really the guy with the answers at the table. Another key concept in Six Sigma is to graph your data. Whenever you have data, you want to exploit it. Graph it in as many possible ways as possibilities that you have. And one of the nice things about SIMUL8, it has the tool StatFit. The thing I like about StatFit, it is a user-friendly, easy tool to use. It's the curve-fitting tool, so I can take my, like John had mentioned, my empirical data set, and I can simply just do a copy, Control-C, copy, and I can just drop it into the data table. And once it's in there, then you can do a curve, an auto fit. It can do the prediction of saying that this represents a beta distribution, some known statistical distribution. You can also change the parameters just through a little dial or a scroll. You can look at the descriptive statistics, but it's an excellent tool. So the bottom line is you definitely want to exploit your data. You want to graph it as many ways as possible. So leveraging statistical distributions, curve fit your data. This is kind of funny because John was in his presentation about the correctional facilities. He was emphasizing that the team there uses empirical distributions. Here in manufacturing, we tend to use our empirical distributions, but we strongly recommend that you do a curve fit and you use a known statistical distribution, and we set up our define our parameters for that statistical distribution. In manufacturing applications, 9 times out of 10 they are going to fit strongly represent some known statistical distribution. So there are plenty of that will allow reduction in your overall modeling time when you use known statistical distributions. You can also then easily black box entire subsystems or segments of your model can be collapsed using these distributions. And then if you're going to go ahead and use an empirical distribution, and, you can always just simply do a drag and drop it in that into a probability profile. At least it's housed in a distribution. So the known distributions, such as, this is just a couple examples of downtime. It's commonly known that we use exponential and Erlang's. In cycle times, we often just use the fixed distribution. That would represent the overall ideal cycle time or the design cycle time of it. And one other point is just a common data collection error is to capture all the points and try to force them into one distribution. And when we do that, you're usually going to end up with some ugly, multimodal distribution. When we're looking at manufacturing facilities, we usually want to find out what a typical hour looks like. So we generally recommend that you filter all your outliers. If you want to look at catastrophic and how the plant reacts to a catastrophic scenario, that can be done as just a special scenario. So definitely want to capture the steady state of a system. So if you ever find yourself in the tornado of change, just remember that the less is more approach is how you'll end up meeting your project timing. This is how large companies like Ford Motor Company are able to shorten their production time and get their product to the market ahead of the competition. And what I've learned over the years is applying just some basic fundamental Six Sigma tools in conjunction with my discrete event simulation steps was really key to being the guy at the table that actually could produce answers in the next set of questions sooner than anybody else. So it truly is like having a crystal ball and seeing into the future. And that's how I was able to conduct several successful studies for a large automotive company. So with that, any questions?
Yeah, so again, everyone, if you have any questions for Brian, please insert them into the chat panel. Brian, we do have a few questions for you right now. We can quickly go over. I did think that's a really interesting topic there, and I think it's worth for everyone to really look into this kind of stuff and apply it to their own simulations. So, considering that these will be the slides online, I think they'll be good to review for any Simulate users. But a quick question for you, Brian. Which of the Simulate elements have you used in the most creative way?
That's an interesting question. I would say that there are several complex, and like we were talking about, conflicting objectives when we're doing manufacturing. And batch build processes and sequencing can become really complex. And I would say the ability to set signals and delay signals, so using a buffer and a work entry point and just sending like add work to queue, so sending just add work to queue and letting that just set off another little section of the model. Maybe that's going to be these little signals accumulating, and when they accumulate to 4 parts or something, then it sends off another signal. So doing this it's a great way. It's nothing more than using a part and a buffer for sending little signals throughout the model, but it's an excellent way to have all these little subsystems at your control, just using some signaling. And I find that was a creative way of capturing. Probably my explanation didn't give it justice, but off the top of my head, there are a lot of complex systems that have been able to be captured
Sure.
with this less is more approach.
Sure, great. I think we have time for about one more question right now, Brian, if that's all right.
Sure.
One of our users has asked, have you ever used Simulate as a tool within a DMAIC project, or do you see any advantages in using DMAIC for simulation projects?
Yeah, I know I've definitely used both. The design for Six Sigma was obviously is a great when you have the opportunity to do a design for Six Sigma project. That's usually the biggest bang for the dollar because you have a green site, a new system. You're trying to design it to be as robust as possible. But equally as important, we have plenty of plants that we're retooling or reusing or just making some changes. So the DMAIC process definitely lends itself. So you're going to be analyzing a current system, and you're going to be doing some improvements to it, and also just the verification and validation at the end, and developing a set of control plans for the plant to use to help reduce such things as overtime and things like that that are required when they start to fail to meet their target. So DMAIC is equally as important as a design for Six Sigma project, particularly in setting up your control plans to keep the plant on hitting its target, and usually it's its target jobs per hour. So that's a good question. Equally as important. Great.
Cool. And I guess again, if there's any additional questions, we can answer them on LinkedIn. I think we have time, maybe just for one more, Brian. A user has asked, how do you go about validating your models?
Yeah, verification and validating, two extremely important pieces. One of them, obviously, you're going to be debugging your code and going through it using some of the SIMUL8 debugging features, but really when it's all said and done and you're validating up against at Ford Motor, I had the opportunity to actually compare our models directly to some of our measurables that were on the plant floor. So we did have some data collection systems in place. We had teams that track these measurables. So that's where that credibility really comes in place, and especially when you're building your model and doing the verification and validation steps, and the team's actually bringing back some data, and your model's actually predicting that. That's where you'll start to get more and more phone calls and emails. They'll want you to be continued on the plan, and you will be the busy guy. So absolutely. And another important piece is you don't ever want to calibrate your model to get there. My models were always such that that they were the team was engaged enough, and these steps are overlapping and so on. So we are always able to hone our models in to actually make them represent the realistic behavior. Like I say, once you start doing that, that's where the credibility really becomes strong. The team starts working, as a solid, unified team.
Great. Well, thanks a lot for that, Brian. Thanks again for your presentation.